Hello, all of you. Welcome to the ninth lecture in the course Analysis and Modeling in Chemical Engineering. In this week, we have been discussing the fundamental laws and concepts in chemical engineering. We started with the equations of motion and we gave different contexts where the equation of motions is used and some examples. Then we discussed the continuum approximation and then we discussed the transport equations, the momentum transport, the heat transport, and then mass transport. And then we looked at the material balance and energy balance and some examples on that. And in the last lecture, we started our discussion on thermodynamics. What exactly is energy? What is work? And then we ended up on the discussion on entropy. So I want to pick up on that discussion and then talk about what we call as energy functions that you may have encountered in thermodynamics. So in the previous example, whatever we did in the lecture, we looked at a system that was isolated. That means that there is nothing done by the surrounding, there is no influence of the surrounding. But then if I look at in what ways we can change the energy of the system, we have taken that the energy was constant when system was isolated. But if we think about what ways we can change the energy, at least we can think about three different ways. The first way is by some means we provide heat to a system, and what the heat is going to do in fact is it is going to essentially raise the entropy of the system provided the temperature is the same. So, let us say for example, if I provide heat to ice, in that case ice will become water, but at the same temperature. So, if I keep the temperature fixed, then the heat is going to raise the entropy, or if the temperature is not fixed, then the heat is going to raise the temperature and so on, right. So, there is a thermal kind of an energy or work that one can do on the system by heating. The other kind of work that one can do is by compressing the system. So, the surrounding may compress the system, there is an applied pressure, and as a result of that pressure, the volume of the system can go from some volume V to something like V minus delta V, right. And when we are doing work on the system, that is I am compressing the system, the delta V is going to be negative, and therefore, the work done on the system is therefore minus P into dV, and that is some kind of a mechanical work. The pressure volume work is mechanical work. And then finally, the third type of adding energy on the system or doing work on the system is by adding molecules. Let us say you have a water solution and you want to add some other component, let us say sugar, right. It is already a solution and you are adding another molecule in there, or let us say you have a pure water and you are adding a new solute species. In those cases, whatever species I am adding, that will lead to some chemical energy that we associate with the idea of chemical potential. Any molecule that we add in the system, it will basically lead to an energy difference equal to the chemical potential, and therefore, if I add certain number of molecules of that species, it is going to have chemical potential leading to an energy change of mu I dni, which we can associate as a chemical energy for component I, and this we can do for different components in the system. Let us say I have methanol ethanol mixture, I can either add molecules of methanol or I can add molecules of ethanol, or I can add some third species in the system, right. So, therefore, there is a summation over the components or species which I am adding, the chemical potential mu I of species I, and the number of molecules of species I which I am adding, right. So, whenever I say capital Ni, I am referring to the number of molecules of species I, but later on you will see I am also referring to the number of moles which I will represent by small n I, right, because the definitions that you may have read in chemical engineering thermodynamics, they could have been in terms of the number of moles, that is typically more used than the number of molecules. So, now if I have to change the energy of the system, we can think of now three ways: a thermal energy change that relates to temperature and entropy, a mechanical energy change that relates to the pressure and volume, and finally, a chemical energy change that relates to chemical potential and number of molecules or number of moles of different species in the system, right. And therefore, we can write the net energy change as sum of these three possible energy changes, right. If, for example, there is a change in the entropy at a given temperature, this will give rise to a thermal energy, TDS. If there is a compression in the system, this will give rise to a mechanical energy minus PdV. And if I am adding something of different species, I am giving rise to a chemical energy in the system. So, this really forms the first, I would say, differential relation that we use in thermodynamics. So, now there is a very interesting notion of this controlled or independent variable and the dependent variables, right. And it is very important to understand what does that mean, right. So, in all the discussion that we will do in this class and in general in thermodynamics, we are considering a system that does not have any kind of like a bulk flow, not like a pipe flow where things are flowing. I am considering systems which are otherwise stationary. Of course, the molecules within the system is still moving. That is always the case. Even if we have a stagnant glass of water, the molecules within that is still moving purely by diffusion, but there is no bulk movement. There is no pressure driven movement or things like that, right. Or there is any kind of mixing, no external agent. So, the only force that exerts between the molecules is the intermolecular forces. That is the only force that is significant and acts on the molecules. There may be gravity, but gravity is not dominant. It is the effect of gravity is very, very less. There may be buoyancy, but again that is also negligible, right. The main force that is present in the system is the intermolecular force, and there is no external agent like that is causing flow or mixing or something. Of course, you have a system and a surrounding, and we will take that discussion further, but there is no external agent like flow, mixing and things like that. So, in that circumstance, one can achieve a condition of thermodynamic equilibrium. And what this means, just like chemical equilibrium, we have said that the forward reaction rate is equal to the backward reaction rate. In the condition of equilibrium, whatever change is happening in any property, let us say pressure, volume or temperature, whatever change is happening in increasing that property, that is balanced by the changes that leads to decreasing of that property. That means the property overall remains constant, right. Let us say, for example, I am looking at a system for which temperature is constant, right. So, there may be processes happening that results in increasing the temperature, and there may be processes that will result in decreasing temperature. So, both these processes are kind of having the same rate. That means that the temperature is staying constant. So, now if I now look at that internal energy again, and I want to again look at it for the system which was isolated, right. And I ask myself, what exactly the energy of this isolated system a function of, right. And then we have like three pairs of variable that we have just discussed in the previous slide that are very, very important here. So, we have to pick one from each pair. I tell you why, right. So, we have variables that dictate thermal energy change T and S. We have variables that dictate the mechanical energy change P and V, and then we have variables that dictate the chemical energy change mu I and Ni, right. And since the chemical potential can be defined for all the components present in the system or all the species present on the system, I am going to put a curly bracket here. And similarly, the number of molecules, I am going to put a curly bracket here. Whenever I do that, basically I am referring to all the chemical potentials for the species mu1 to, let us say, some mu c, and similarly number of molecules n1 to, let us say, nc. So, now the energy of the system is constant, and in order to control the temperature of the system, if I have to, how exactly we will do that? I mean, we need to probably attach some kind of a heat source or a sink that basically can control the temperature, right. Let us say I want to control the temperature of this particular room, then One of the ways is something like putting an air conditioning in the month of summer, or some kind of a heater in the month of winter, right? So in order to control temperature, we need to basically attach something that can provide or take away heat. But we have assumed that the system is isolated. That means that the surrounding cannot do anything. So what will happen in this case? If there is no energy exchange with the surrounding, then what is going to happen? And we have given examples of this effect earlier, that the system will try to maximize its entropy, right? And thermodynamic equilibrium will be defined as the state of maximum entropy, right? So we are going to have maximum possible entropy. And what is that entropy a function of? That entropy is going to be a function of the energy. Why is that? You remember the example, I was basically distributing the quanta of energy between different particles present in the system, right? So if we have certain energy, then we have certain number of quanta available, and there are certain number of ways in which I can distribute in a manner that will maximize the entropy of the system, right? So for a system for which energy is kept constant, in that case the number of quanta available is also constant, and when we maximize this ways of distribution of that, that means we will maximize the entropy of the system, right? So we can say the system has an entropy that depends on the energy of the system, that defines how much quanta are available, and of course the number of particles in the system, because these are the particles in which I am distributing this quanta of energy. And now again, since you have certain number of components, I can say the number of molecules of each of that component. And finally, I gave an example of the mixing. The entropy was dependent on the volume, because volume defines the room that is available in the system, right? So when a system is isolated, in that case I am going to maximize this quantity entropy, that is a function of energy, that is a function of the number of molecules of each of the component, and of course a function of the volume, right? So now since entropy is a function of these three, I can therefore also say that energy is a function of entropy, volume, and number of molecules of all the species, right? What does it mean to have an entropy that is a function of three variables? Essentially it means we have a function of four variables, S, E, and I, V, right? So if we have any relation, any kind of function for this quantity, by suitable arithmetic manipulation, I can convert it to a function of energy as a function of entropy, number of molecules, and the volume, right? And if I now do that, and I recall whatever argument I made just now, three kinds of energy, thermal, mechanical, and chemical, I will go back and use this thing, d is equal to TdS minus PdV plus summation of mu I dni, right? So now if I have to find the energy change in the system for any particular process, it is going to be given by integrating this particular differential relation. Now I just told you the system is isolated. So what does that mean, that I will do an energy change in the system, right? So the point here is we will not look at the energy change for this particular system. We will consider two different isolated systems or many different isolated systems, and we will look at the energy difference between those two, right? Just to make my point clear, let us say I look at two isolated system. One is having energy E1 and other is having energy E2, and one is having volume V1, other one is having volume V2, and one is having a certain number of moles, let me call it Ni1, and other one is having certain number of moles Ni2. So I am referring to the energy change between these two, energy difference between these two, right? The reason I am doing that is because in both these cases, in this case my energy is a function of the entropy in that state, the volume in that state, and the number of molecules in that state or for that system. And in this case again, E2 is a function of S2, V2 and Ni2, right. I am looking at an energy change between these two states, right. That is my delta E. So, essentially what I am trying to say is the fact that we are studying an isolated system, we have the ability to consider a system where I can control the volume, the energy and the number of molecules, or by extension the volume, entropy and the number of molecules, right. So, I can prepare a system for a given choice of volume, energy and number of molecules, and I can prepare another system with a different volume, energy and number of molecules, right. So, I have the ability to therefore prepare different isolated systems with different value of these variables, right. So, what are the independent variables here? These are the variables which we have ability to control, and if I express this in terms of energy as a function of variables, then the independent variables are the entropy, the volume and the number of molecules, right. And what they then have to do is, as I have expressed here, I need to basically construct functions of temperature as a function of entropy, pressure as a function of volume and chemical potentials as a function of number of molecules. How will I do that? I will basically perform studies on two different systems that has entropy S1 and S2 that will give me temperatures T1 and T2, and if I do it for three systems S1, S2, S3 entropy, I will get temperatures T1, T2, T3. So, in that way basically what I am doing, I am computing the temperature T for a given value of entropy. Entropy becomes the independent variable and temperature becomes the dependent variable. So, I am basically trying to find temperature as a function of entropy, and now I can extend it to a large number of experiments for a large number of isolated systems that I can prepare, and I will get temperature as a function of entropy. And this, if I integrate, I get the thermal energy contribution of delta E. Similarly, I can prepare the system with different volumes and I measure the pressure for those systems, and by doing that I can construct a function of pressure as a function of volume, right. And if I integrate that, that will give me the mechanical energy contribution for that system. And similarly, I can do for chemical potential for every component in the system, and again that will be a function of the number of molecules of that component in the system, and by doing that I can get the chemical energy contribution, right. I already told you that isolated systems are practically impossible to prepare, because any system I will make, it will have some mass or energy exchange with the surrounding, right. So, although I said that I can do an experiment with many different isolated systems and get temperature as a function of entropy, pressure as a function of volume, chemical potential as a function of number of molecules. Theoretically, there is no problem in that, but practically speaking, it will be very difficult to create a system that is isolated, that does not exchange energy or mass with the surrounding, right. So, then we think about an alternate way of looking at it. And what we do, we change the control variables, right, and it is possible to do that, right. So, we have defined internal energy E, and for that my dE has been already defined. I define a new quantity now which I will call enthalpy, and that is equal to E plus PV. So, now my dH will be dE plus PdV plus VdP. So, basically what I am doing, I am using the fact that d of PV is equal to PdV plus VdP, right. An expression of dE we already have from there. So, I plug it in and I get the expression of dH. And what has happened here? Now, the independent variables are entropy, pressure and number of molecules. Volume is no longer independent variable here. Now, the pressure is an independent variable. That means I have the ability to control the pressure in the system, right. That means I can prepare systems which are at different pressure. Maybe 1 atmosphere, 2 atmosphere, 5 atmosphere. In the previous case of isolated system, the volume was fixed and volume was determining the pressure. Now pressure is fixed, pressure is controlled for the system and volume is found as a function of pressure. Again, I can prepare now different systems which are corresponding to different pressures, and then I can compute the energy change, which is now enthalpy change, where we will need something like volume as a function of pressure, temperature as a function of entropy again, and chemical potential as a function of number of molecules. So, I have not touched the first and last term, I have only touched the second term. Earlier, for this case, I was computing pressure as a function of volume and integrating with dV. For different systems I was preparing. Now, I am computing for this case volume as a function of pressure and integrating with respect to pressure, right. So, the control variables are changed and I am looking at different systems now, where instead of volume in the isolated system, I have the ability to control pressure, right. I can extend this idea and define another variable where the objective is to basically change the entropy with temperature. In the same way that we have changed the volume with pressure here, now I want to change the entropy with temperature. How do I achieve that? I define a variable f, which I will call the Helmholtz free energy, that is E minus Ts. And again, d of Ts is equal to Tds plus SdT, and I use the expression of dE, put it here, and now I have a new expression. Again, similar to the expression of dE, what has changed is now we have minus SdT as opposed to Tds that we had here. So, now I will compute here entropy as a function of temperature and change temperature. This will be a system where temperature is the independent variable. I have the ability to control temperature, which we refer as isothermal system, right. What is important here when I am looking at an isothermal system, what I am saying is that I have the ability to control temperature. So, if I can run the system at 25 degrees Celsius, I have the arrangements of heating and cooling whatever is required to achieve a temperature of 25 degrees Celsius. For the same setup, because you already have the arrangement, we can also do the experiment at 50 degrees Celsius or 75 degrees Celsius. So, basically the independent variable or the control variable in the isothermal system is temperature, and we will compute entropy as a function of temperature as opposed to temperature as a function of entropy in the earlier case of isolated system. And now you can imagine this is more practically relevant case, because isolated system is almost impossible to prepare, but isothermal system we can prepare. In fact, the room I am standing in, we have an air conditioning and we can set the temperature to a value that we desire, and we can have the temperature controlled around that. So, isothermal conditions are easier to achieve as opposed to isoentropy condition, that means a constant entropy that will be achieved only when the system is isolated. Now, I can go further and I can also think about doing both at the same time. So, now I want to change the first term and the second term. So, I want to change entropy with temperature and I want to change volume with pressure, and I can indeed do that. What I will do, I will define a new energy G as the Gibbs free energy H minus Ts, and again d of Ts is the same as what we have defined earlier, and I will plug in the definition of dH that I have obtained earlier, and then I will get a new expression for dG minus SdT plus VdP plus mu I dNi, right. And now we have a function where the independent variable is temperature, pressure and number of molecules. And now it may seem natural why we use Gibbs free energy a lot, or you may have heard of Gibbs free energy a lot, because a typical experiment that you may have heard of or a typical problem statement that you may have seen, you have temperature and pressure conditions defined. If I want to operate, let us say, a chemical reactor or a distillation column, I want to define the temperature and pressure conditions. That means I have the ability to control the temperature by maybe a thermostat, and I have the ability to control pressure by, let's say, having a barostat, right? So therefore, I want a definition of energy for which temperature and pressure are the independent variables, right? And that energy definition is the Gibbs free energy, right? So it is therefore very important to understand why we have so many energy functions: internal energy, enthalpy, Helmholtz free energy, Gibbs free energy. These four different energy functions simply refer to four different contexts of a practically realizable system. If we have an ability to control temperature and pressure and the number of molecules in the system, that means it's a closed system where temperature and pressure is getting controlled, I will go for the Gibbs free energy. If on the other hand, I have ability to control temperature, volume and number of molecule, I will go for the Helmholtz free energy. If I have the ability to control the entropy, pressure and number of molecules, I will go for enthalpy. And finally, if I have the ability to control entropy, volume and number of molecules, I will go for internal energy, right? And they all exist in pairs. So I cannot control both together. If I control entropy, I cannot control temperature. Temperature becomes a function of entropy. If I control pressure, I cannot control volume. Volume becomes a function of pressure. If I control chemical potential, I cannot control the number of molecules. That becomes a function of chemical potential, right? So as soon as we make one of each pair as the independent variable, the other becomes a dependent variable, right? So 2 points here. The first point is that if I simply replace this capital Ni with a small ni, now I am referring to the number of moles as opposed to number of molecules. And I was talking about these three pairs, Ts, Pv and mu I Ni. What is interesting to note here is in each of the pairs we have one intensive variable that does not depend on quantity, and one extensive variable that depends on quantity, right? So temperature is intensive. Even if you increase the quantity, temperature will not change. Pressure is intensive, independent of quantity, and chemical potential is also a property that is intensive. And entropy is going to increase as quantity is increased, volume will increase as quantity is increased, and number of molecules will increase as the volume is increased or quantity is increased, right? So S, V and I, these are extensive, and T, P, mu I are intensive, and I can choose one from each pair as the independent variable, other becomes the dependent variable, and the way we choose it, we get different energy functions. I don't have all the energy functions possible listed here, but these are the most common that we find. So let's recap with one example problem. So on the left, I am giving you systems and we have to match with the corresponding energy function. In the first case, it is given that it is constant volume. That means volume is a control variable. There is no mass exchange. That means the number of molecules are also independent or a control variable. And there is no energy exchange, so there is no way we can control temperature. Entropy has to be the control variable. And in this case, naturally, we will go for internal energy that has these three independent variables. Second case, we have constant pressure. So pressure is a control variable. No mass exchange, again the number of molecules is a control variable, and there is no thermal energy exchange. That means again temperature cannot be controlled. I can control the entropy again, and this will correspond to the case of enthalpy. And third case, we have a closed system. So that means that the number of molecules are fixed. There is no mass exchange, also written here. So number of molecules are controlled. Constant pressure, so pressure gets controlled. And finally, constant temperature, temperature gets controlled. As we have just seen, this will correspond to the Gibbs free energy of the system. So now we can go ahead and take these equations that we have derived, and based on the simple calculus, we can identify the different properties or derive the expression of different properties that we are interested in, right? I will take an example of the differential equation we have got, differential relation we have got for dg, but the same thing can be done for other expressions also, right? So for this particular expression, if I, for example, control or keep p and ni fixed, if I keep the p and ni fixed, this amounts to dropping the second and third term here. So now I am left with dg is equal to minus s dt, right? And that is for fixed value of p and ni, right? So now if I take a derivative of this, that will correspond to a partial derivative for the fixed p and fixed ni, and that is equal to clearly minus s from the expression that we have here, right? I can do something else. I can keep the temperature and Ni fixed. So now I will be left with dg is equal to V dP, and again if I take a derivative, the partial derivative, this will give me the volume V. And finally, I can keep the temperature fixed, pressure fixed, and other than I, all other number of molecules, all other component number of molecules I keep fixed. So I will be left with something like dg is equal to mu I d and I. You see the summation is gone here because the number of moles of all other species other than I are held fixed. So in that case, we will get the expression of the chemical potential, that is defined as partial molar Gibbs free energy, and that is what it comes from, where it comes from. And again, I can always replace the number of molecules with the number of moles, right? How will we get these energy functions G, H, E and all that? They need to come from the equation of state. An equation of state is derived typically by experiment, and we get a relation of pressure, volume and temperature. We can use that relation to derive the expression of G, H, E and so on, and there is a whole lot of arithmetic that goes there, like Maxwell relation and all that, that helps in that. I will not get into that. It's not by no means a replacement of full-fledged thermodynamics course, but just to give you an idea of what are the equation of state. The ideal gas law is PV equal to nRT, and then this is an example of the van der Waals equation of state, right? So typically for any substance, you will know its equation of state from the previous experimental data. If not, one can perform the experiment to find the equation of state. That's the pressure, volume, temperature relation. Plug it in these kind of equations, whatever I have shown you, or something derived from here, and you will get the expression of the energy functions. And once you have the energy functions, technically you can get all the other properties that we are interested in, let's say enthalpy, the Gibbs free energy, the pressure, temperature, number of molecules, chemical potential, whatever we don't know, that we can possibly evaluate if I know the equation of state for that system. So I will not go into examples of that, but this particular idea of why we are using 4 different energy functions or even more than that is very, very important. So now I am going to pretty much end with the laws of thermodynamics, right? Typically this is covered first, but I hope by now you will have more appreciation of this. There is a 0th law that serves as the definition of temperature. It simply means that for any thermodynamic system, I already told you that kinetic energy corresponds to temperature, but this is a formal definition. For any thermodynamic system, a system of molecules, we can define a quantity called temperature, and it defined in a manner that the temperature defines the thermal state of the substance, right? So let us say, for example, if I have 2 different systems and they have the same temperature, I will say that they are in a state of thermal equilibrium. Thermal equilibrium means that something must be same in those 2 systems. And what is same? The temperature of that system, right? And by extension, we can say that if TA is equal to TB and TB equal to TC, then TA must be also equal to TC, right? This is a mathematical logic kind of a statement, but the point it is trying to make is that the state of a substance must be defined by some quantity. Only then we can say what is thermal equilibrium, right? The thermal equilibrium is defined as a state where temperatures are equal, right? So if temperatures are equal in thermal equilibrium, so when A and B are in equilibrium and B and C are in equilibrium, then A and C must also be in equilibrium because they share the same property, temperature, right? That's the 0th law of thermodynamics. The second law, we already have used it earlier, that is given by this: the energy change is given by the heat that we add to the system and the work that we do on the system, right? In this case, I am not referring to chemical work, it is typically used for pure systems, right? So, delta Q it becomes my TDS and delta W typically becomes minus PdV. So, this gives me dE is equal to TDS minus PdV for a pure system, but if I have a mixture, then we also have to consider the mu I dNi, but that will be considered some kind of chemical work that we are doing on the system. But typically, this definition is typically used for a pure system. And finally, there is a second and third law that correspond to entropy. Second law states that the entropy of the system and its surrounding together makes up the entropy of the universe, and that cannot decrease. The entropy of the universe cannot decrease. There may be a possibility that entropy of a system is decreasing. For the isolated system, I told you entropy has to be maximized, but it's not generally true. I can reduce the entropy of a system. For example, ice is having a lower entropy than liquid water, but I can always freeze liquid water and make it ice. That is very much possible. I can do that for a system, but whenever I do that, if I look at the entropy change of the system and the surrounding, in that case the atmosphere or the refrigerator, the total entropy change must be none either higher than 0 or equal to 0. When it is equal to 0, we have a reversible process, otherwise we have an irreversible process, but in no circumstance the entropy change of the universe, system plus surrounding, can be negative. And finally, there is a third law that basically sets the, I would say, the limits on the entropy, right, or a definition of the lower limit of temperature. What we say that the entropy at 0 Kelvin temperature is equal to 0. What does that mean? If I am really at 0 Kelvin, I am definitely in a solid state, and in that state too, we pretty much have no movement of atoms or molecules which are present there. Even in a solid state, the molecules can in principle vibrate, or atoms can vibrate around their positions. But when I am in the limit of 0 Kelvin, I am in a perfect crystalline state where there is no vibration at all of the molecules present. It defines the lowest possible limit of entropy. Entropy cannot be negative for sure. Entropy change can be negative, but absolute entropy cannot be negative. And the lowest possible entropy is at 0 Kelvin, where the average V square goes to 0, the velocities goes to 0. So, therefore, the temperature goes to 0 and entropy in that case also goes to 0. And we can therefore see that how the laws of thermodynamics prevent the creation of a time machine, because entropy of a universe must always increase, right, or remain constant. You can imagine that universe is not a reversible process, right. So, since the entropy is always increasing, so therefore, unless it is reversible, which probably it is not, you will have many irreversible processes in the universe. You cannot go back, because if you go back in time, you are basically reducing entropy, and that is not allowed by the law of thermodynamics. The only fundamental law that is violated if you create a time machine is the second law of thermodynamics, that says that the total universe entropy can always remain constant only for reversible process, but if you have any irreversible process, any irreversibility, then entropy of a universe must always increase, right. So, you can imagine that from starting from Big Bang, if you look at the time axis from Big Bang, the entropy has been increasing. We were in lowest entropy state when the Big Bang happened, and today we are in a higher entropy state, and in the future we are going to be in a state of even higher entropy, and so on, right. Okay. And finally, I have already said that the entropy of a system need not increase in a chemical process. What is true from second law is delta S of system plus delta S of surrounding has to be greater than equal to 0. This can very well be negative, provided this is sufficiently positive, right. So, it should not give you an impression that entropy must always decrease in a process. That is not true. Entropy of the universe cannot decrease, right. So, with that, I am going to stop the discussion on thermodynamics. In the next lecture, we will start talking about the laws of chemical kinetics and chemical equilibrium. With that, I stop here. Thank you so much.